Hello everyone, I welcome you all to the course of heat transfer. In today's session, we will discuss some of the problems related to condensation. The first problem goes like this. A vertical cooling fin approximating a flat plate 40 centimeter in height is exposed to saturated steel at atmospheric pressure with a saturation temperature of 100 degrees Celsius and HFG, which is latent heat, is equals to 2257 kilojoules per kg. The fin is maintained at a temperature of 90 degrees Celsius. We need to calculate the thickness of the film at the bottom. Second one is overall heat transfer coefficient or average heat transfer coefficient. Now, if you look into the chapter of condensation in your heat transfer data handbook, you have different cases for which you have different expressions. It could be vertical surfaces, it could be horizontal tubes, there could be bank of n number of tubes, there could be vertical tubes. For every case, you have different expression or formula. Now, from the statement of the problem, it is clear that it is a vertical surface and the height of the surface is 40 centimeters. Now, if you look into the formula corresponding to vertical surface, you have delta x, which is boundary layer thickness, is equals to 4 times of mu into k into x multiplied by Tv minus Ts divided by G into HFG multiplied by rho square whole to the power 1 by 4 or 0.25. Now we will look into each terms associated with this expression. In this formula, mu suffix L is nothing but dynamic viscosity. K is thermal conductivity. X is distance along the surface. It is measured in meters. Tv is vapor temperature. Ts is surface temperature. G is acceleration due to gravity. The value is 9.81 meter per second square. HFG is latent heat of vaporization. It is measured in joules per kg. And rho is density of the fluid, which is measured in kg per meter cube. Now, one care has to be taken while noting down the value of HFG. Generally, we use the unit of kilojoules per kg, but while substituting in the equation, it should be in joules per kg. So that is why I insist you to go through the expression from the data handbook. At the same time, the unit in which you need to substitute, that also you will understand by referring to the data handbook. Now he has given in the problem the relevant fluid properties. It could be density, which is 965.3 kg per meter cube. Thermal conductivity is 0.68 watt per meter Kelvin. And dynamic viscosity is 3.153 into 10 to the power minus 4 Pascal second or Newton second per meter square. Now these units should be same. If they have given in some other form, we should convert them into the main units. Now, if you consider the equation for the thickness of the film at the bottom, he has asked. He may also ask thickness of the film at the center of the vertical surface. In that case, this x will be equals to height divided by 2. Now we have seen the total height of the plate is 40 centimeter. You convert it into meters, so it is 0.4 meter, provided if it is asked at the end or at the bottom. He may also ask the thickness of the film at 1/3 of the height. In that case, you should divide height by 3. He may ask at 2/3 of the height. You should multiply height with 0.66 or 2 by 3. Now if you substitute the values for mu is 3.153, k value given 0.68. In this case, x is nothing but the distance along the surface. So he has asked us to calculate the boundary layer thickness at the bottom. So I need to consider the x to be 0.4, which is height of the vertical surface. Now TV is nothing but vapor temperature. So he has given the saturation or the saturated temperature is 100 degrees Celsius and the surface temperature is 90 degrees Celsius upon 9.81, which is G value. HFG he has given 2257 kilojoules per kg he has given, but we need to substitute in joules per kg, hence we have multiplied this with 10 to the power. So multiplied by density x square, which is 965.3 x square, whole to the power 1 by 4 or 0.25. If you substitute the values, you will get the boundary layer thickness as 0.1136 mm. I'm repeating, the boundary layer thickness is 0.1136 millimeter. Now the second bit of question is to calculate the average heat transfer coefficient, and in the same data handbook we have also given the expression for average heat transfer coefficient. H is equals to 4 by 3 into K by delta X. This K by delta X is nothing but local heat transfer coefficient. We have a relation with average heat transfer coefficient and local heat transfer coefficient as average heat transfer coefficient is equals to 4 by 3 times local heat transfer coefficient, and local heat transfer coefficient is given by K by delta X, where K is thermal conductivity, delta X is the boundary layer thickness, and it has to be substituted in the unit of meter, not in mm. So that care has to be taken. And if you have a practice of identifying the units out of the data handbook, you will not make any mistake. Now, if you substitute the value of K as well as boundary layer thickness in terms of meters, we will end up with a value of average heat transfer coefficient as 7981.22 watt per meter square Kelvin or watt per meter square degree Celsius. These kind of problems are very simple. We just need to substitute the values. Only thing is, first you should identify a proper equation which one needs to be used, and the units in which the properties must be expressed. If you take care of these two parameters, then solving problems on condensation is very easy. Now we will look into another problem, again on vertical plate. A vertical plate 500 mm height and maintained at 30 degrees Celsius is exposed to saturated steam at atmospheric pressure. You need to calculate the rate of heat transfer here. Second bit is the condensate rate per hour per meter of the plate width for the film condensation. He has expressed in detail, and you can use the properties of water at mean film temperature for these values, as the density could be 980.3 kg per meter cube. Thermal conductivity 66.4 into 10 to the power minus 2 watt per meter Kelvin. You can consider a value of 0.664 directly. Dynamic viscosity is 434 into 10 to the power minus 6 kg per meter second he has given, which is not familiar as per our regular units that we use. The regular units that we use for dynamic viscosity is Pascal second or Newton second per meter square. Now, if you deduce the unit of Pascal second or Newton second per meter square, again you will end up with this simplified unit, that is kg meter per second. You can reduce that. It means that if you express the dynamic viscosity 434 into 10 raised to minus 6 Pascal second is same as 434 into 10 raised to minus 6 kg meter per second. This you can do out of your basic knowledge on unit conversion. And the latent heat HFG is given as 2257 kg per kilojoules per kg. Now in this case, the first question asked is, you need to calculate the rate of heat transfer, as well as second one, the condensate rate per hour per meter of the plate width for film condensation. Now it is not necessary that he should give the value of properties all the time. In some problems, you need to get the values from the data handbook, and that will be considered at film temperature that we are going to discuss in next problem. Now again, if you need to calculate the rate of heat transfer, you need to know the value of H, and the H value is calculated as follows. Now if you look into the data handbook for film condensation, the value of H is given by this expression, that is H is equals to 0.943 into K cube rho square G into HFG upon mu into L into TV minus Ts whole to the power 0.25, where K is thermal conductivity, rho is density, G is acceleration due to gravity, HFG is latent heat, it should be substituted in joules per kg. This is dynamic viscosity, L is length or the height it could be as it is a vertical surface. TV is vapor temperature, Ts is surface temperature. And if you substitute the values in the expression, we'll end up with the H value as 4242.8 watt per meter square Kelvin. Many students do this mistake that they will calculate all these values, but they will forget to take the fourth root of that value. So keep this in mind. You need to take the fourth root of this entire value. Then multiply that with 0.943. You will have a H value as 4242.8 watt per meter square Kelvin. Once we know the value of H, we can easily calculate the heat transfer, which is given by Newton's law of cooling, Q is equals to HA into TV minus Ts. Now H value we have obtained here. Area is nothing but 0.5 into 1. 0.5 is the height, 1 is the assumption for the width, because if you see the problem, he has said per meter width of the plate. So we need to consider the dimension of the vertical plate as 0.5 into 1. The same has been taken here. If you consider the temperature difference of 70 degrees Celsius, you will end up with the value of Q as 1,48,498 watts, which is joules per second. If you convert it into kilojoules per hour, you'll have a value of 534.6 into 10 to the power 3 kilojoules per hour. Now the second bit of the question is, you need to calculate the condensate. You know the formula Q is equals to M into HFG, where HFG is the latent heat. Now how much amount of condensate you have got, if you need to calculate, you just need to reverse the equation. M is equals to Q upon HFG. You have Q as 534.6 into 10 to the power 3. It is in kilojoules per hour. If you divide it by HFG, which is in kilojoules per kg, you will have the condensate rate in terms of hour as 236.8 kg per hour. Moving to the next problem. In this case, I have considered a horizontal tube. The problem statement goes like this. A horizontal tube of outer diameter 20 mm is exposed to dry steam at 100 degrees Celsius. The tube surface temperature is maintained at 84 degrees Celsius by circulating water through it. We need to calculate the rate of formation of condensate per meter length of the tube. In this problem, he is not given the values for different properties. In such case, you need to get the values at film temperature, and the film temperature is calculated as Tv plus Ts divided by 2, or the average temperature of vapor temperature and surface temperature. This is also given at the top of the formula in your heat transfer data handbook. So if you take the film temperature, which is 92, you'll end up with, because the steam temperature is 100 or the vapor temperature is 100 and the surface temperature is 84, if you take the average, you have 92 degrees Celsius. Now the properties at 92 degrees Celsius has to be considered. In your steam table or in your data handbook, if you search for the properties, you may get at 90 degree or you may get at 100 degree, but it will not be at 92 degrees Celsius. In that case, you need to take a linear interpolation. As you all know, x minus x2 divided by x1 minus x2 is equals to the corresponding property values. And if you get the property values at 92 degrees Celsius, the density is 963.4 kg per meter cube. Dynamic viscosity is 306 into 10 raised to minus 6 Pascal second or Newton second per meter square. Thermal conductivity is 0.677 part per meter Kelvin. Similarly, properties at saturated vapor, you have density of vapor as 0.596 kg per meter cube, and the value of latent heat is 2457 kilojoules per kg. Now, if you consider the value of vapor or the density of vapor in comparison with the density of the liquid, is very negligible. Hence, many a times this density term will not be considered in the expression. Again, for a horizontal tube, if you look into the heat transfer data handbook, under film condensation, you have H is equals to 0.728 K cube root square G into HFG divided by mu into D, where D is the diameter. TV minus Ts whole to the power 0.25. Again, you should substitute the value of HFG in terms of joules per kg. Rest all values are known to you. If you substitute, you will have a value of H as 11,579.7 watt per meter Kelvin. Now this H is nothing but average heat transfer coefficient or overall heat transfer coefficient. Now the question asked is heat transfer per unit length. We need to take the condensate actually. Before that, we need to calculate the heat transfer per unit length. You know, for a tube, we consider the area to be pi d into L. As it is per unit length, we need to multiply only with pi n d. H into A is nothing but pi d multiplied by the change in temperature. If you substitute the value, H value we have obtained pi 3.142, D is diameter, which is given, will end up with a value 11,641.2 watts. And the question he has asked, the condensate, you just need to divide the heat transfer per unit length by the latent heat. If you calculate, you will have a value of 5.157 into 10 raised to minus 3 kg per second, or if you convert it into kg per hour, you need to multiply by 3600, in which case you will have the condensate 18.56 kg per hour. Now, if you observe, the value of H we obtained in all the problems is much higher compared to the post-convection. As we have discussed, in condensation or in boiling, the value of H will be very high. Now with this, I will stop here. Thank you.